Modern engineering and STEM fields move fast. To keep up, they require professionals who can adapt to unpredictable variables and solve problems independently. But the foundational instruction feeding these industries, specifically higher mathematics at the university level, remains static. This schematic shows the traditional explanatory lecture. Information flows in one direction, from the lecturer to a grid of passive nodes, the students. This treats students as stenographers, recording information without the cognitive development needed to apply it creatively. The input method of traditional technical education misaligns with its required output. We are training stenographers for fields that require architects. Researcher T.A. Romanchuk argues that fixing this systemic failure requires an immediate transition from an explanatory approach to a cognitive one. The specific pedagogical tool used to force this cognitive transition is problem-based learning. Most STEM educators assume this method belongs strictly in the practical seminar or the laboratory, where students are already working hands-on. Romanchuk argues the exact opposite. Problem-based learning is actually more critical to integrate into the dense, theoretical lecture format. To prevent students from passively transcribing complex theory, instructors have to deliberately re-engineer the lecture hall. It must become a space of intellectual friction and contradiction. The overarching goal of a problem-based lecture is to create a highly controlled environment where students realize their current mathematical toolkit is inadequate. This cyclical architecture has 4 stages. Stage 1, problem awareness, recognizing a knowledge gap. Next, problem formulation, posing a specific, inescapable problem. Stage 3, hypothesis generation, driven collaboratively by students, not the lecturer. Finally, verification, testing the hypothesis against the initial problem, completing the cycle. The burden here falls entirely on the instructor. They must design the specific mathematical trigger that forces the lecture hall into that first stage of awareness. Executing this 4-step cycle successfully takes students who were once passive receivers of axioms and makes them the active architects of those axioms. The first method for generating this lecture friction is presenting a direct mathematical contradiction that breaks the student's current rule set. Take a foundational scenario students bring from high school, solving a standard quadratic equation. We map the discriminant on a standard real number line. When the discriminant is less than 0, we hit a barrier. Calculation cannot proceed. The traditional student reflex to this dead end is declaring no real roots and abandoning the problem. Here is the instructor's intervention. They halt the lecture and ask what happens if we search for a solution beyond real roots. This prompts the lecture hall to hypothesize the existence of an entirely new number system, just to bypass the dead end. By deliberately withholding the immediate introduction of the imaginary unit I, the instructor forces the students to organically discover the necessity for complex numbers on their own. A second method for designing lecture friction forces students to reverse engineer mathematical models they already understand. This illustrates a baseline calculus concept. Differentiating the law of motion, SFT, flows forward, yielding velocity, VFT.
The friction point is the inverse problem. How do we determine the original law of motion when only velocity is known? Students must now use collaborative reasoning to untangle this inverse kinematics problem in real time during the lecture. Working backwards through this specific, tangible physics problem leads the class to deduce the existence of the antiderivative. The lecturer only formally introduces the operation of integration after the students have discovered it as the mathematical inverse to differentiation. Grounding an abstract mathematical operation in a reverse-engineered practical problem ensures deep conceptual comprehension rather than rote memorization of integration rules. The third method of integrating this framework into lectures requires students to actively complete or derive formal mathematical definitions. In this scenario, the lecturer writes only the baseline algebraic definition of a vector cross product on the board. The geometric meaning of this product is deliberately omitted. The instructor challenges students to derive the geometric meaning themselves by mapping high school parallelogram area formulas onto this new concept. This active derivation forces students to deduce the conditions for vector collinearity. If the area shrinks to 0, the vectors must be parallel.
This exact scaffolding method extends naturally into deducing coplanarity through mixed vector products later on. When students actively assemble complex mathematical definitions from prior knowledge, they retain the underlying geometric logic. This process helps prevent the eventual loss of algebraic formulas through memorization. Let's look back at the schematic of the lecture hall. It now functions as a space of active cognitive dialogue and debate, with information moving in both directions. But Romanchuk warns that this model has limitations. It is highly sensitive and is not a universal solution. The first critical variable is the student's baseline knowledge, which is heavily impacted by their high school preparation and internal motivation. The second critical variable is the size of the cognitive leap required to solve the problem posed by the lecturer. This chart plots baseline knowledge against the cognitive gap required. Success depends on the balance between these two. If the required gap far exceeds the baseline knowledge, we hit a failure zone. If an instructor fails to accurately calibrate this gap, the entire mechanism collapses. Students cannot synthesize a new hypothesis if they lack the foundational axioms to build it. Navigating these constraints successfully requires massive preliminary design work and scaffolding from the instructor. The ultimate goal of this immense effort is teaching the culture of mathematical discourse, training students to argue, defend, and verify their own hypotheses. Moving problem-based learning into the lecture hall requires treating the classroom not as a delivery system for facts, but as a space for active derivation. The practical seminar is a place to practice using mathematical tools, but the lecture hall must be the forge where those tools are created. True efficacy in teaching higher mathematics comes not from flawlessly explaining concepts to an audience, but from meticulously engineering their struggle to understand them.